Hello, ladies and gentlemen. Today we will be talking about geometric sequences. We have talked about arithmetic sequences and series. Today we shift to another major type of sequence and series called a geometric one. And these are terms that are separated by a common ratio. If the ratio of two consecutive terms is constant, then we call it geometric. And the way we find that common ratio are, we take un plus 1 and we divide it by u sub n. So take any term and divide it by the term immediately preceding it, and that will give you the common ratio, and that should be the same for any pair of terms. If it's not a common ratio. It's just a ratio between terms. So if we have a first term u1, the second term would be that times the common ratio. So this is term number 1. This is term number 2. What would term number 3 be? Well, it would be term 2 multiplied by the common ratio, so u1 times r times another r, so u1 times r squared. The fourth term, what would that look like? Well, I hope that you're thinking, well, it's going to be similar to this, similar to these other three, but what exactly will it be? Well, it'll be the first term times the common ratio to the third, and so on and so on. And I could have you keep listing these until you turn blue, just like the ink on the screen. But I'm curious, what would the nth term be? What would a generic rule for this geometric sequence be? So look at a pattern. This is r to the first, it's the second term. This is r squared, it's the third. R cubed, it's the fourth. So the nth term, the exponent of r, will be 1 less than that. So n minus 1. So a generic rule, an explicit form for a geometric sequence, is un equals first term times r to the n minus 1. So we're going to skip A. If you want to do it, go for it. I think it's too elementary for us here. Find the common ratio and write the next two terms of each sequence. Okay, so how do we find the common ratio in B? We take the second term and we divide by the first term. So that's negative 1/6 times 2 over 1. This ratio is negative 1/3. And before we can say it is the common ratio, although we are told it's a common ratio, but before we say that, we should check that it's the same for the next two terms. So we should do 1/18 divided by negative 1/6 just to verify that this is indeed negative 1/3 also. So r for this sequence is negative 1/3. And how do we find the next two terms? Oh, we just keep multiplying by 1/3. So for part B, u sub 4, the fourth term, is going to be this times negative 1/3. So that would be negative 1 over 54. u5, the fifth term, would be positive 1 over 162. So there's our next two terms. What do we do for C? There's no numbers. Oh my goodness. Well, that's okay, guys. To find the common ratio, remember we're taking the second term and dividing by the one immediately before it. So our common ratio is 2a squared. Hopefully, we should verify that it's the same between these two terms. So 4a to the fifth over 2a cubed 2a squared. Same. So that means we do indeed have a common ratio. C is indeed a geometric sequence. So what are the next terms? Well, u4 will be u3 times 2a squared. So 2 times 4 is 8. And then a to the 7th. u5 is going to be 8 times 2, or 16. A to the 9th. All right, so let's talk about series, ladies and gentlemen. A series is when we add up all of these terms. So S sub n is equal to u1 plus u1r plus u1r squared plus u1r cubed plus dot, 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 all the way out to the nth term, adding them up. And this n, this subscript, determines how many terms of the sequence we're adding. So with an arithmetic series, we had a quick, nice rule for adding these up. We didn't actually have to add all of the terms. Let's develop this a little bit and see where it comes from. Now, I'm going to write down another sequence, or another series, and this series is going to be this top series, but multiplied by the common ratio. So r times s sub n, which would be this first term times r, which is here, second term times r, which is here, third term times r, which is there, and so on and so on. And this last term times r is u1 r to the n. And if we subtract these two lines, we get a lot of these terms crossing out. This one would cancel with the one above it, and we're left with 1 minus r times s sub n equals u1 minus u1 r to the n. And over here we're just factoring the s sub n out. So what can we say? The sum of n terms of a geometric series is, well, if we solve for s sub n, we get this formula. S sub n is the first term times 1 minus r to the n. We factor out the u1, and then we're dividing by 1 minus r to get s sub n by itself. Now, if the common ratio is a fractional value, if it's between -1 and 1, this r to the n is going to approach 0 for very, very large values of n. So as n gets huge, this thing effectively becomes 0. Because if a number less than 1, a fraction, raised to a huge number, is going to get smaller and smaller and smaller and approach 0 as n goes to infinity. So if we have an infinite series, if n is going on and on and on and on, and the series never ever ends, and r is between these, we actually have a sum. The sum of an infinite series will converge, or we say it's equal to, the first term divided by 1 minus r, because remember, this thing, this term in parentheses, is getting closer and closer and closer to just 1, that thing that my cursor was on top of. This is just becoming 0 as n gets really huge. And this is only valid when that's true. A lot of times you'll see associated with this formula, absolute value of r is less than 1. And these two formulas, they are in your formula book, just like the arithmetic sequence in the series, and that explicit rule that we had for a geometric sequence is also in your formula book. So let's boogie. Calculate this geometric series given by the sum from 1 to 6, 3 times 2 to the r. Now, we could do this the long way and write out all the terms. So 3 times 2 to the first plus 3 times 2 squared plus 3 times 2 cubed plus da-da-da-da-da. But if we can recognize that this is a geometric series, if we can recognize that this rule right here fits with the form un equals u1 r to the n minus 1, we can move a lot more efficiently. And you might say, well, this is r up there, it's not r minus 1, it doesn't really look like this, but that's okay, it still follows the same rule. We're multiplying by 2 to get from term to term. The difference is, this 3 is not the first term. The first term is this whole thing. The first term is 6. So in terms of our rule, u1 is 6. And r is 2. So S6, we're adding 6 terms. We're going from 1 to 6. This is going to be equal to the first term times 1 minus 2 to the 6th over 1 minus 2, and we can crunch these numbers. Now, we can also do this straight up in our calculator. If I press this button, you will see right here a summation function. And we can put in r equals 1 to 6, 3 times 2 to the r. We push enter, and there we have it. It's that quick. 378. So there we go. If we were going to do this anyways, we're going to be using our calculator to do 2 to the 6th hour, unless you really, really want to do that by hand and then multiply that by 6. Personally, I don't want to. So if I'm allowed my calculator and I have a problem like this, I'm going straight to this function in the calculator, typing it in carefully, and getting my answer. It's far more efficient than doing it out by hand. Geometric series get very large very quickly. All right, find 2 possible geometric sequences where the sum of the first 2 terms is 9 and the sum of the first 4 terms is 45. And write down the general term, that means write down the rule of the sequence. All right, so u1 plus u2 is 9. That's S2. And S4 is 45. Now, I wrote S2 as u1 plus u2 because we could write that as u1 plus u1 times r. And we could take that and solve for u1. Rearranging this rule of factoring u1 out and then dividing by 1 minus r, or 1 plus r I should say, we get the first term to be equivalent to 9 divided by 1 plus r. Now S4, that's a little bit longer of an expansion. I'm going to use my sum formula, u1, 1 minus r to the 4th, over 1 minus r. Okay, well, how'd that help? Why did I bother writing all this stuff down? Well, if you look here, we can substitute. We have an expression for u1. We have 2 equations. We're given 2 pieces of information. There were 2 unknowns that we need, u1 and r. I have a system of equations that I'm solving by substitution. So 45 equals 9, 1 minus r to the 4th, over 1 plus r, 1 minus r. Now we get to solve this, guys. And you might be looking at this going, whoa, this thing looks scary. Well, one approach we could take is we could use the graphing calculator. If this is a GDC type question, we could put 45 and we could put this mess in to another function, find the intersection of the 2. But there's a little bit of clever manipulation that we can do. The denominator is a difference of squares factorization. If we expand this, if we FOIL it out, we get 1 minus r squared. Now the numerator has a difference of squares that I can factor. 1 plus r squared, 1 minus r squared. And hopefully you're jumping up and down in your seat right now saying, I see why you did that. The 1 minus r squareds cancel. We're left with 45 equals 9 times 1 plus r squared. Divide by 9. 5 equals 1 plus r squared. 4 equals r squared. R could be positive or negative 2. Notice it says each sequence. Find 2 possible geometric sequences. So I have my common ratio. Now I need the first term for both of these. So I knew that U1 was 9 divided by 1 plus r. Let's go 1 plus 2 first. So this is for r equals 2. I got 9 over 3, so U1 is 3. So UN is 3 times 2 to the n minus 1. Or we could let r be negative 2. Nine over negative 1. So my first term in this case is negative 9. So my rule for this would be UN equals negative 9 times negative 2 to the n minus 1. Now, this is a problem where you have to pay very attention to the verbiage in the question. How is it written? It's telling us there are 2 solutions. Well, what kind of equation do we know gives us 2 solutions? Quadratics. So you should be expecting from the get-go that you're going to have to solve a quadratic equation somewhere, and that's right here. So last example we're going to talk about in this video. The sum of the first n terms is given by Sn equals 5 to the n minus 1. Find the first term and the common ratio of this series. Well, remember, S1 is going to be the same as the first term. So let's find S sub 1. Five to the first minus 1, which is 4. Now, if I knew the second term, I could find the common ratio. Well, I can find the second sum, the sum of the first 2 terms. Remember, that's A1 plus A2. It's going to be 5 squared minus 1, so that's 24. Well, if the first term is 4 and the sum of the first 2 terms is 24, that means the second term is 20. And then the common ratio is going to be the second term divided by the first term. 20 divided by 4, that is 5. So my first term is 4, and the common ratio is 5. And that's all it asks me for here. And with that, ladies and gentlemen, I will leave you to have a wonderful time working on these problems.